All right, thank you everyone for joining us on today's webinar, Bringing AI Research to Wireless Communication and Sensing. My name is Ben Stone and I'm with RCR Wireless News. In this webinar, Qualcomm AI Research presents an overview of state-of-the-art research at the intersection of the two fields and offers a glimpse into the future of the wireless industry. Your speakers today will be Arash Bhuti, Machine Learning Research Scientist, Senior Staff Engineer Manager, and Daniel Degman, Machine Learning Research Scientist, Principal Engineer, Qualcomm AI Research. As a note to everybody, the webinar and the slides will be made available for download after the presentation today, so please be sure to enter any questions that you have for Arash and Daniel during the presentation as well. We'll do our best to answer them or follow up with you after the webinar via email. With that, I'm pleased to give you Arash.
Thank you very much. Thanks everyone for joining this webinar. It's my great pleasure to talk today about machine learning research for wireless with my colleague Daniel. We're going to talk about how machine learning and wireless can complement each other and how machine learning can improve communication, how it can improve sensing, and what future holds for us in that regard. Let me start by just talking a little bit about wireless and about machine learning. So wireless design has been done traditionally by using tractable mathematical models. We have interpretable solutions. And as you can see from the state of our technology, our models, our solutions generalize very well to different deployment conditions. You go, you get your smartphone, turn it on, and it works. And that means regardless of the channel condition, we manage to get a good performance out of the models that we have. So our abstractions manage to generalize well, and our models actually adapt quite well to new scenarios and to new situations. That's the strength of the wireless communication. On the other hand, if you look at machine learning as state of machine learning research, machine learning algorithms, they do excellent jobs at learning a specific task from a specific data set. They make accurate predictions. They manage to learn very complicated generative process, for example, for image generation. And at large, they are excellent at sensing and perception tasks. So here already we can see how we can enhance our wireless algorithms designs by bringing machine learning and applying it properly to what we want to do. And this is not just a conjecture. Qualcomm is already pioneer in that regard. We have the first 5G AI processor in Snapdragon X70. It's an AI-enabled wireless modem. And Qualcomm Wireless Research demoed a lot of different solutions, enabling AI ML for air interface design with showcases that you can find in Mobile World Congress. So we already know that this is an exciting area that has a lot of potential and a lot of different topics to work on, many promising directions to look into, and it has a lot of potential for using AI research, machine learning for enhancing 5G in different fronts. But technological innovations, they do not come for free. They come with their own challenges. And we want to highlight a few of these challenges and then, trying to show in this presentation how we are able to address some of these issues. The first thing is generalization, out-of-domain generalization. As I said, machine learning algorithms, they are excellent at learning to do a specific task. And then when they have to generalize to different tasks, the problem becomes challenging. But what we want to do and what we do in wireless is we need to generalize. We need to be able to operate in different conditions, in different channel conditions and scenarios. The other problem is adaptability of ML models. We get a single ML model that works on a specific scenario, but we actually want to have an ML model that can work on different scenarios. And it's not about just changing a specific environment. We want to change communication parameters, number of antennas, transmission power, all those things. And our model should be able to adapt to those situations easily. And the last item is supervised learning. So supervised learning, meaning you have a teacher that supervises your model, tells what it should learn. So getting that teacher for all scenarios, it's difficult, close to impossible. We cannot just have all different scenarios. And when the environment changes, we just cannot go and gather data and build a new model again. So what we want to do, we want to be able to move away from supervised learning, try different ideas that enables our agents to learn in a more unsupervised, we could supervise, or self-supervised way. And in this webinar, we're going to explore some directions, some of our research that pushing the wireless innovation by addressing these constraints. I'm going to talk about communication, and my colleague Daniel will talk about RF sensing. And let me go ahead and start talking about wireless communication. So machine learning, in order for machine learning algorithms to enhance wireless communication, in order to improve that, what the key idea is, we cannot abandon domain knowledge. We cannot abandon the years of experience we have in designing and building wireless systems. What we need to do, we need to utilize that effectively to build and design our models. And I'm going to show how this happens we do two different examples. One is about modeling communication channels. The other one, designing communication systems. Let's start with the key component of wireless design, wireless channel. Wireless channel is complex. It contains a lot of propagation effects, reflection, blockage, all sorts of things. And you can see that the configuration of each space affects the way channel behaves. It is complicated, but it's the core thing for wireless design. We need to understand how channel works. We need to model it properly, and we need to estimate it. These are the key components that we need. This becomes even more important for machine learning research, because with proper modeling of communication channels, we can understand better, gauge better gains coming from machine learning algorithms. So how we modeled communication channels traditionally? Well, either we start working with general abstractions, we try to build simplified models, use distributions and the mathematical tools that are easy to deal with, and then prototype it like that. We can have some hard-coded assumptions about the number of different reflections we have, about the different scenarios that we want to consider. And if you want to build a specific channel model for a specific environment, it requires a cumbersome field measurement, getting a specific devices, gathering all the measurements, making assumptions. So all in all, this is a complicated task, and scientists did a great job so far working on it. However, neural networks already provide an interesting direction to tackle this problem. We can use the flexibility of neural networks to build so-called neurochannel models. They can model complicated functions. In this case, our channels. They are fast. We can rapidly sample from them, and we can work with simple traces. We can just make the model learn from just simple traces, not requiring specific hardware. What we don't want to lose in our design is interpretability. So how are we going to address that? First, let's understand what communication channel is. A communication channel can be adequately represented by a function called impulse response. This impulse response basically captures different passes that you have in your propagation environment, different gains that you have in each one of those passes. And the impulse response, knowing the impulse response, you can say, given an input signal, what would be the output signal of the channel? So to model the channel, we need to understand these, to model properly these parameters. And then when it goes to frequency domain, that's what's needed for our communication. We need to understand what happens in the frequency domain, frequency response of the channel, which is the Fourier transform. And these informations are actually crucial also for sensing and positioning applications. And my colleague Daniel will cover some of it later. Now, what happens is that we can have an input signal, then the channel represented by impulse response basically does a convolution with the input signal and provides the output signal. But we don't know the channel. So what we want to do, we want to get a neural network that learns this input and output mapping. However, we want to have two things in our design. We want to have interpretable network, and then we want to have a variable number, deal with variable number of antennas at the input and output. And that's how we're going to do it with our design. So what happens is, instead of just training a black box neural network to model our channel, we're going to directly model impulse response. Neural network is going to generate us a complex distribution over impulse responses. And that idea, the idea that we just don't abandon classical assumptions, they don't abandon domain knowledge, but we try to augment, enhance it with a neural network. This is the idea of neural augmentation. This is the guiding principle for our designs. We try to always see what happens classically and how we can do better. So how we can design such a model? We can use innovations in generative modeling research of machine learning. And in this specific case, we're using generative adversarial networks for doing that. The generator actually generates our channel. And in order to make it adaptive, we just learn antenna to antenna channel gains. And the way generator learns to generate good channels is by having a discriminator that acts as a teacher and teaches the generator to generate good examples. The task of discriminator is comparing what comes out of our neural network and comparing it with what have from real world, and train and tell is good or not, and then get the model trained. Interestingly, the discriminator itself can use domain knowledge for picking proper features. For example, spatial correlation, the correlation between antennas, it plays an important role in modeling multiple antenna communication. And that's what we're going to tell discriminator. We can say discriminator should pay attention to spatial correlation. And in that way, we can improve our model. So both in terms of what is generated and what is discriminated, this is an important task. So what happens? We have an input signal, which is transmitted over a channel. We get output of that channel. We just have access to X and Y's. We don't know the channel. Then we want to get this impulse response. We want to learn the distribution of this impulse response. So we get a Neurochannel model that can be used to simulate the same channel. And what it learns to generate is the impulse response, as you see. And prototyping this idea on standardized 3GPP channel models, we can see that the MIMO-GAN, the model that we have proposed, actually does a great job in doing that. This is about communication channel modeling. What we need to do is also channel estimation. Communication channels, as you see, they're complex objects. They're very difficult to estimate, but we need to know what channel is in order to properly communicate over them. So, for example, if the channel changes rapidly, we have a very dynamical scenario, we need to be able to track the channel. What happens to the channel when we're moving around? But we cannot just lose our resources and monitor every time. So what we're going to do once in a while, we're going to get some measurements, call it using so-called pilot symbols. We're going to get some measurements and have access to those measurements. And then on top of that, we're going to track the channel in the meantime. So you might say, how are you going to do that? Well, classical Kalman filter proposals are already away. If the dynamic that we have, the changes that we have, follows a fixed distribution, Kalman filter can have a set of parameters adapting to that specific dynamics, and actually does a very good job in tracking the channel in between. However, the Kalman parameters needs to change when the dynamics change. In this case, dynamic is Doppler frequency. When the velocity changes, Doppler frequency changes, and all those things. And the challenge is that we cannot use just a single Kalman filter to address this problem. This is the main challenge. A single Kalman filter cannot address all situations. So what we just need to have many different Kalmans to deal with dynamic scenarios when the speed changes and all those things. But we like Kalman. Kalman is interpretable. It gives us confidence. It generalizes well for a single dynamic. So we want to keep those features as well. So one might say, okay, neural networks are very powerful. So let's get a neural network and train that network over many different scenarios. And the network itself can actually just have a single model for all these different scenarios. So this is a black box approach. Get a neural network, recurrent neural network that tries to predict the channel. Unfortunately, these type of designs, they are not very robust to changes in the observation frequency. They're not very robust to changing in the dynamics, basically on-scene dynamics. And also, they cannot naturally take care of situations where the observation is not available, because the network wants to use the observation when it's there, but wants to skip somehow when it's not there. And neural networks like LSTM and RNN, they cannot organically deal with that. So if you like Kalman so much, if you think Kalman is great, and the idea is, we want to adapt Kalman parameters for two different dynamics, we can actually use the expressivity of neural network to update Kalman parameters. Instead of doing the whole task itself, we say, we know Kalman is doing a good job. We have a lot of interpretability there. So let's try to, instead of replacing Kalman, let's try to augment Kalman with a so-called hypernetwork that updates the parameter of Kalman based on the dynamics that it sees. Now, with this, we keep the interpretability of Kalman. We get the nice generalization properties of Kalman. We have expressive power of neural networks used for updating Kalman parameters, and also different robustness characteristics of Kalman is preserved. So let's look at one experiment here. We have a channel, it's changing in time, and we want to see how well our neural augmented Kalman filter works. So the plot that you're seeing, these are the gain that we are getting from the Kalman. As you can see, the best gain comes from our neural augmented Kalman, the hypernetwork Kalman. And LSTM in this case follows quite closely what we have from hypernetwork Kalman. So you might think, okay, LSTM is doing a good job, but one point to keep in mind is that LSTM has been trained on the exact same data, with the same frequency of pilots, with the same dynamics. The problem appears when we move away from that. So in this case, the plots that you see on the left, these are what we saw in the video. In this case, LSTM does a good job. It had seen everything in the training data, and it does a good job there. However, when we move to scenarios where the frequency of observation, so-called pilot ratio changes, or where the Doppler changes and has not been seen by LSTM, LSTM loses performance significantly. And you can already see how bad the gain can be in those cases. But our neural augmented Kalman continues to perform well. So with this type of design, we get the best of both worlds. And the idea was, let's keep our domain knowledge. Let's try to see how we can use neural network to enhance it, and then build the model as a unit. And that's what we call neural augmentation. One last comment is, if we just get the neural augmented Kalman and train over all the data, of course, it's going to outperform Kalman with exact known dynamics. So it's going to be like the best of the best that you can get from that. So this basically, from channel modeling to communication design, this shows how machine learning for wireless can be properly done by incorporating domain knowledge and designing our ML algorithms intelligently on top of that. So with that, I switch to my colleague, Daniel, which is going to talk about a lot of sensing and positioning applications.
Thank you, Arash. Let me share my screen. So, so as Arash said, I'll be talking about RF sensing. So you might remember this slide from earlier in the slide deck where you saw a person sitting between a transmitting and a receiving device and all the different paths that the wireless signal could take. And all those different paths, they are encoded in the channel. So in a way, you could say that anything that is within a reasonable distance of the transmitter and receiver is encoded in the channel information. So the trick in RF sensing is how do you get that information back out? Because then the promise is that we can detect locations of devices, positions of human subject, detect their gestures or activities, opening all kinds of new use cases. In particular, in this webinar, I'll be talking about positioning, because that's a very huge use case, right? So I'll be talking about active positioning, by which we mean that we are trying to position a device that is actively emitting communication signals. So you can think about this like as a cell phone or a robot or an autonomous vehicle that's using communication. On the other hand, I'll be talking about passive positioning, where we're trying to position a person or an object that is not emitting RF signals. Instead, what happens is you take the transmitting device, it sends something to the receiver, and then this person or object in the middle influences the channel, and through that we can detect it. So you can think of that as a kind of radar. But first, let us focus on active positioning. There are lots of use cases. The most appealing to myself is indoor navigation, because it's so nice nowadays. You can just walk outside with your phone and use GPS and the map to find your way around in any city or environments that you're located in. But indoors, this doesn't work so well. So imagine you're in a big airport or a conference center. You want to know your way around. The GPS is a very weak signal. It doesn't get inside the building very well, and propagation of the RF signal inside this building is very complicated. So that's like a huge use case where 5G or Wi-Fi positioning can help. The same is true for vehicle navigation. Sometimes you might be like in an underdoor parking garage or in a tunnel, and then GPS doesn't work. Besides that, there are like applications in industry, like tracking of autonomous robots in warehouses, or you can go even further, that you apply a little 5G tag to each box in your warehouse, allowing you to know the location of basically each item that you have in stock. So how does this positioning work? Well, we're kind of in the context of 5G. So we're going to assume that there are indoors a number of access points, or TRPs, transmission reception points, as they're called in 5G. You're going to have a number of them, and they are synchronized. So they have a shared notion of time up to like nanosecond resolution. Also, their positions are known from during deployment, their positions were measured. Okay, so now we have a device that's indoors trying to localize itself. It's going to emit a reference signal, and the TRPs, the access points, are going to register the channel that they measure from this reference signal and turn this into the channel impulse response. So in this channel impulse response, you see this big first peak. That's like when the signal first arrives. And the empty space before it is like the propagation delay. How long did it take for the signal to arrive? So if you measure this signal from multiple access points, you can form a kind of triangulation. It's not quite as simple as triangulation. I'll get back to that. But basically, you do triangulation to figure out the location of the cell phone. But you might also notice in these impulse responses, there are little extra peaks following the big main one. So those are like the multipath components where the signal bounced off some wall or floor and then arrived slightly later at the access point. This is also what complicates positioning. So imagine there's something blocking the line of sight between the cell phone and an access point. Then the wireless signal will likely find a way to get to the access point. Will be through some reflection. And this path will be longer than you were expecting from the line of sight. Also, the channel impulse response will be much more cluttered, as you can see here, because reflections are generally weaker than the line of sight. So you have to take this into account when you're analyzing the signal. So to test all this technology in San Diego, we have a test setup in a big warehouse with 6 of these access points, an autonomous robot who's driving around with a cell phone mounted on a robot arm. So we can measure the channel and know the exact position of the robots and perform all kinds of experiments. And 2 of these experiments, they were showcased in our MobileBot Congress 22 demo. Using two different techniques. So the first technique for positioning that we use is called time difference of arrival. It's kind of a classical technique using digital signal processing, so no machine learning in there. And when I said that you can do triangulation, and it was not quite so simple, it turns out the only thing that you can measure, because the phone is not synchronized to the system, the only thing that you can measure is the difference in arrival time of the signal from the phone at each of the access points. And if you compute that and you solve the equations, then you'll find out that the phone is on a kind of curve, a hyperbolic curve, between the two access points. And if you do that measurement between many access points, you get kind of multiple intersections. So the phone must be, or the UE, somewhere located at this location. But the great thing about this is that you don't need any labels or any training data or any initialization to get this to work. If you know where the access points are, it works. But the downside is, as soon as there's a non-line of sight condition, that's going to make the path longer, so the delay will appear longer. It's going to push the phone away from the access point. It's going to think that it's further away. If you don't handle this, it's going to be less accurate in non-line of sight. And also, it doesn't use any of the multipath information. So you could think of the multipath as a distraction, but actually it can also be a source of extra information. So that's where the other methods comes in. It's called RF fingerprinting, because basically what you're doing is you take the fingerprints of the channel impulse response at a particular location, and then you learn to map that to that location position. And it's called ML-assisted RF fingerprinting, because in our case, we were using a machine learning model that maps from channel impulse response to precision. The upside of this is that it's like way more accurate than the temporal difference of arrival, which you can see in the top right corner over here. Like the mean error is in the order of 20 centimeter, the positioning error. But the downside is that you need all these labels. So you need a robot or a volunteer to walk around with a cell phone, which is equipped with a precise measuring device to know the location. So this takes a lot of effort. And then to make it even worse, if something changes in the environment, your trained model will not be valid anymore. So you need to redo this data capture. So in our work, we are exploring how can we get the best of both worlds. We want high precision, but not use very many labels. So that's where our work on RF SLAM comes in. It's illustrated in this picture here on the right. So suppose you have some cell phone or a robot who's transmitting this reference signal to the access points. So you have the line of sight, but likely there will be walls and floors in the neighborhood. So you will also see the reflected signal. And you can think of that reflection as if there's actually an extra access point that you can use for positioning. And there might be multiple of these, like one corresponding to each wall or floor around you. So the first key idea in this model, RF SLAM, is that you can use this multipath propagation to actually position yourself better. And you can even do it when you have just a single access point available to yourself. And the second idea is that if you collect this data at enough locations in the environment, so you move your UE, your cell phone everywhere, then there's only one unique feasible solution to this optimization problem. And you only need to collect unlabeled samples, right? So you don't need any labels for this to work. So the actual model is shown here on the left, but first let me focus on the picture on the right. It's the same picture as on the previous slide, but now the icons have been replaced by symbols. So P is the location of the cell phone that we're trying to determine. P0 is the location of the access point. P1 is the first reflection, but there might be additional reflections, P2, P3, and so on. And then H is the channel. Okay, so what this model is going to do, it's going to take the channel, run it through a learnable neural network, which will have to predict the 3D position. But we're not going to tell this model explicitly what 3D position it has to predict. Instead, we're going to say, okay, if this is the location you predict, then we run this through a hard-coded propagation model. So this model knows about the physics of RF propagation. And then we can reconstruct the channel again. And we're going to say, okay, the input channel and the reconstructed channel, they should be identical, or that's going to be your machine learning training objective. And there are a few knobs to the propagation model, which are going to be the learnable locations of the reflected access points. So you're going to optimize this whole system end to end, and then it will converge to, it will figure out where are the reflected access points, and what is the position for each channel location. And of course, you could add a bit more knobs here, like if you want more sophisticated physics. So this slide shows the results in a 3D ray tracing simulation. So we take a very large room with just a single access point and simulate a channel at many different locations, run it through the model, and the accuracy is about 44 centimeter accurate for 90% of all the locations or users. And no labeled CSI values had to go into this model because we use this propagation model. So we use this prior knowledge of how RF propagation works to make this work. So that's a great strength of this model, like no labels required thanks to this hard-coded physics model. But it's also the weakness. So if the hard-coded physics model doesn't exactly match reality, then your results in a real deployment are going to be slightly off. And this is a nice bridge to the next section where I'll be talking about passive positioning, where we kind of use a model-free approach. So there will be no assumptions about the RF propagation, instead only very weak assumptions about what kind of data we're going to expect. So let me switch to the next section. Will be on passive sensing, or passive RF sensing, and specifically passive positioning. So as you see in this animation on the left here, if you have a transmitting device and a receiving device, then anything in the environment will be captured in the channel, including a human who might be walking through the signal. And by analyzing the signal, you can figure out what was the location of the human, what gestures was he making, even things like respiration and other vital signs can be detected. But the signal propagation is relatively complex. So that's why we use self-supervised and weakly supervised machine learning to get the information that we want back out of the channel. So if you're able to figure this out, there are like a huge number of use cases that are opening to you that you could start to exploit. So the first one is everything around positioning and detection of presence and action. It can be used to like automate your home or your enterprise, or count how many people are in a particular meeting room or in a particular area of your retail store, and so on. And you don't need any cameras. So in that sense, it has better privacy than camera-based solutions. A second class of applications is where you can detect gestures that people are making. So you can use that to control your phone or your laptop. Or you could, for instance, have your laptop turn off as it senses that you walk away and turn back on, again, as it senses that you're approaching it. In healthcare, there are also applications like measuring vital signs or monitoring your sleep or detecting when an elderly person might have fallen. And even in automotive, you can do things like detect if a baby or a pet has been left behind unattended in a car, and then send some kind of alarm to the owner of the car. And you can measure whether the driver is actually paying attention while he's sitting behind the steering wheel. Right, but back to positioning. So our model, so like the unsupervised model for passive positioning, is called Y-cluster because it has this clustering component that makes it work. And it was designed from the ground up to work with real data collected on real hardware that you see in the bottom right corner here. So this is close to commercial hardware with special instrumentation, so we can capture the channel easily. But it does positioning under non-line of sight conditions, and no exact 3D labels are required. The only thing you need to do when you initialize the system initially, you need to give it a floor plan, which makes sense because without a floor plan, it doesn't make much sense to position yourself if it's not relative to anything, right? And you need to walk around the environment where you want the system to walk, while you use an app to tell the system what room you're in. So you're going to walk through your living room and then say, I'm in the living room. Then you go to the kitchen, say, I'm in the kitchen, walk up the stairs. You say, like, I'm walking up the stairs. And meanwhile, the system will record the corresponding channel packets. As I said, so this was like a heavily real-world experiments, and we validated in 3 different environments. 2 of them were like offices with a floor area of about 15 meters by 20 meters. And the 3rd environment was an actual home of an employee in San Diego, where we deployed 3 access points, so 1 on the ground floor and 2 in the upper floors. And the office environments have one transmitting access point in the center and 3 receivers scattered around the environment. So here you see the actual model illustrated. So I think it's best to describe it with the picture on the right. So the channel state goes into the model. It runs through a ResNet, as you saw before in earlier models. So this is a trainable neural network, and it's going to produce a latent space. So it's some high-dimensional representation of the input data that has been condensed. Then we project that using another trainable neural network layer to a 3D location. So this is the final answer that we're actually interested about. But to train this, we don't use any precise labels. Instead, we have like weak assumptions that the data is living on some manifold. So the input, which might be very high-dimensional space, is mapped ultimately to a 3D space. And we say the first loss that we use, so the first training signal, is the triplet loss, which says if something is close in time, it must also be close in space, so in your reconstructed 3D location. And on the other hand, if it's far away in time, it's likely to be far away in 3D location. So this already helps map the space a little bit. But then we have this additional clustering component, which works as follows. We take all the predicted 3D locations and we cluster them into groups, which then get integer labels. And we ask the neural network model to predict from the latent space these 3D labels. And we also run this mechanism the other way around. And we found, or we designed it this way, because we wanted the mapping from latent space to 3D location to be bijective. So none of the space should map back onto itself. Each input location should result in a unique 3D output location. So if you run the top model, which is like fully self-supervised, so no labels required, you will already see that the rooms and hallways and doorways and such are appearing, but everything will be slightly distorted because there's nothing to tie it down to the real world. So that's where the bottom part, the weakly supervised part, comes in. So we say, give us the floor plan and a few labeled packets. And then we have an additional training signal, the zone loss, which will kind of drag each part of the space that's created at the top here to the right location. And then it turns out that this works very well in practice, as you'll see in the following 3 slides. So this first slide shows the results in the first office environment. So it's a video that was made for our Mobile World Congress 21 demo. So you see the person walking around. So this is the ground truth data. And then the blue dots that are appearing around him are the predicted locations. And on average, they are about 1.2 meters off, which is relatively good in this very large environment. And one particular moment I wanted to highlight is this hallway where the person walks to in the end. There's no line of sight to any of the access points. It's actually quite far away from any access point, and the system continues to work. Then in the second office environment, I wanted to highlight something about very strong non-line of sight. So the colors, so on the left, you see the ground truth that was collected. So that these colored lines, that's where the person walked. And on the middle part, you see the inference results, which are like quite close. Again, the mean error is like only 1.1 meter in the offices. But there's one particular zone in this floor plan, which is the conference room, which I'm actually sitting in right now. It's surrounded by concrete walls. And there's no access points inside the conference room, right? All the access points outside. And then you see that the system degrades somewhat, right? It's not reproducing that loop that you see here. But still, it's relatively graceful, degrading to a mean error of 2.1 meters. The final result I wanted to highlight is in the actual 2-story home. So the goal of this experiment was to do zone classification. So we simply wanted the model to predict what zone the person was in while he was walking the home. But as a byproduct of the Y cluster model, we get actually like a approximate 3D location of where the person is walking. So this area corresponds to the living room. This pink purple area here corresponds to the kitchen. But what I found particularly remarkable in this reconstruction is that the stairs has a part in it where the person kind of walks horizontally, and it's actually found recovered in the reconstruction, which was made without any precise labels. Yeah, so that's it for the RF sensing results. We're now going to go to the conclusion. And I think back to Arash, right?
Thank you very much, Daniel. So we showcased here how machine learning can be used to enhance communication and can be used for RF sensing. And the key ideas we had in mind was first trying to look at unsupervised learning methods, not requiring so many labels for doing our task, trying to incorporate inductive bias about physics of propagation, about the good classical models, incorporating all that into our design in order to get better generalization, keeping interpretability, and also being able to adapt to different situations. Now, this is not all that is about machine learning for wireless. So if you look next slide, in the next slide, you will see that, yes, here. So there is an interesting synergy between sensing and positioning problems and communication problems. Similar to machine learning, classical machine to machine learning. In machine learning, computer vision extracts objects and information from the image, and computer graphics renders those information back into 3D objects and images. So this similar synergy can be considered for wireless. With sensing and positioning, we can extract information about the environment and use that to build channel models to improve our communication. And this synergy of sensing and communication is something that is a fundamental area for machine learning to jump onto, because exactly there it can use a lot of its tool set to design new technologies. Yeah, so I think going to the last slide, we showed how AI can be used for enhancing wireless communications. We talked about neural augmentation, we talked about sensing, supervised, self-supervised and unsupervised sensing, talked about inductive biases there. And at Qualcomm AI Research, we're doing fundamental research on applying AI for RF sensing and communication, but not limited to that. A lot of other exciting stuff is happening, so I encourage you to always take a look at what we're doing.
Great. Well, I think we do have some time for questions. So yeah, I guess my first question, neural augmentation sounds like an interesting machine learning tool. How do you decide where to insert neural networks into traditional wireless algorithms, and which sort of problems are best suited for machine learning?
That's a very, very good question. First of all, I would say neural augmentation is a guideline. It tells us look at the classical models, and whenever you have a parameter in your model that can be learned, that requires tuning, it's a great candidate for applying neural augmentation. Kalman parameter was an example of neural augmentation. Channel impulse response was another example. So all in all, at the end of the day, everything is problem dependent, but looking at this problem, you can see what is really the bottleneck of our system and design, and how actually neural augmentation can help improving that by just augmenting those parameters.
Okay, great. Interpretability of AI is a major topic for the tech industry these days. Is this necessary for machine learning in wireless? And how do we understand when machine learning introduces errors worse than the traditional method?
Yeah, that's an excellent question. So what I can say here is interpretability is important for system building. If you build a system and everything works, then we are all happy. However, when it stops working, you need to find a problem. And without having interpretation about functionality of your variables, it's very difficult to debug them. And it directly impacts the robustness of algorithms there. And overall, what I can say is that machine learning can always help us learn flexible models, better distributions, solve complicated problems, and exactly there that it can bring gains to wireless communication. What we want to keep is interpretability as much as possible.
Okay, great. Question from the audience: how easy is it to get data in wireless? In computer vision, there's a lot of labeled images that were used as data, but has it been done in wireless?
Yeah, so let me talk first about the communication part, and Daniel can chime in on the sensing and positioning part. On the wireless part, there are a lot of exciting efforts ongoing on gathering data for wireless. I think this is also crucial for designing and developing our next technologies. What I can say is that operationally, they might have similar difficulties. Someone has to go gather data, label the data, and all that. However, technically, wireless is more challenging because you need, in general, specific devices. You need to know which hardware you have used. The configuration that you use for getting those measurements can have a lot of impact on utility of that data. If you have chosen the wrong hardware or wrong setup, the data might be completely useless. This might happen in computer vision, but it's probably less frequent. If you have decent images and decent labels, probably it's good enough.
And then for the RF sensing, there are several possibilities. So the first one is you can just buy off-the-shelf radar equipment. So like OFDM radar, you can buy these kits for experiments. So you could use that to collect data. But then if you want data that's like from Wi-Fi devices, that's where it gets more hacky. So there are several chipsets where people have figured out, like, okay, for this particular chipset, if I run it on Linux or whatever, I can extract the channel state. But luckily for that case, there is an upcoming standard, 802.11bf, which is specifically about Wi-Fi sensing. So in that standard, they're going to define an interface for how to retrieve the channel state from the Wi-Fi hardware, and also do that in a way where you can tell the Wi-Fi hardware to behave properly for sensing. So normally, communications hardware is only optimized for communications, and this actually turns out to be pretty challenging for sensing if the communications is constantly changing the channel gain or changing other parameters. So in the standard, you're going to be able to say, hey, please don't mess around with the channel. Just give me the purest measurements that you can do and expose them to a higher level API. But it is an upcoming standard that's currently under development.
Thank you both. Will impulse response work for nonlinear channels, say multiplicative baiting with RIS-based wireless?
Yeah, that's an excellent question as well. So impulse responses naturally work for linear systems. That basically kind of captures the linearity of Maxwell equations, if you want. So that's how we get that linearity. For any nonlinearity, it can be because of, for example, hardware distortion. We need to approach it in a different way. But then I would say it becomes more favorable for using neural networks, where we can learn, again, complicated distortion models and channel models for nonlinear stuff. But to answer the question, channel impulse response supposes linearity of our communication channel.
Awesome. Does the neural network go beyond domain knowledge to expand it? Does it point to areas that we may not consider to improve the output? So what I can say about this is that first of all, you need to have a competitive baseline to properly understand what machine learning is telling you, because sometimes you might report numbers, you might see gains that are just because you have not properly explored baselines, good enough baselines. But even there, if you suddenly see a huge gain, that might already indicate that
there is a gap in domain knowledge and indicate that we need to understand where this gain is coming from. For example, let's say if the neural augmented Kalman is outperforming Kalman in certain scenarios, why this is happening? Is it because the dynamics cannot be properly modeled using typical autoregressive models? Or what is the reason behind that? So machine learning in that sense can be used to expand domain knowledge by showing gaps that were ignored before or because of the computational limitation remained unnoticed. So that's also, I think, an interesting direction for exploration.
Awesome. For passive positioning, what's the required density for APs to achieve a certain level of accuracy? The ratio of APs to floor plan footage at certain accuracy in test environment, etc.
Yeah, that's an interesting question that you actually looked at ourselves. So it turns out in practice that the density at which we have to place the access point matches the density that you would do for a regular deployment. So we're able to see this, right? In offices, we can just see, okay, the normal infrastructure access points are located here, and we put our access points at similar locations, and then it works. But I do have to say for passive positioning, because you have like this two-way, so it goes from the access point to the person and then to the receiving access point. A lot of signal power is lost in that step. So we would actually expect you would need to make it twice as dense. But in our experiments, it turns out that, well, the density that's already there in the building, if we match that, then it's good enough. So basically it would boil down to, yeah, something like 7 or 10, well, let's say 10 meters between access points in an office environment.
So here's an interesting question. Any thoughts about teaming up with cleaning robots, such as Roomba, for location measurements, in that Roomba makes detailed floor maps and is Wi-Fi connected?
Yes, that's certainly a possibility. I'm not in the know of that we're actively exploring that, but there are papers out there that showed that you can do Wi-Fi positioning, so active Wi-Fi positioning for robots specifically. So that's a very good use case, and also you could do things like the robot could see people and the environment around it using RF sensing.
Awesome. You mentioned that Y cluster is the first weakly passive positioning technique. Do you see new research popping up to make it completely unsupervised or easier to deploy?
I haven't seen like easier to deploy, but certainly there are like papers that are continuing. So we had a second paper on this, but the same set of experiments. We had a different approach, which used optimal transport, and then people are continuing that work and building upon it. So yes, it's like a continuous track of research.
Which of all the technologies you presented is closer to going to market? For the passive positioning, it's actually already on the market. So it's in a simpler state than we have been researching, but simply detecting whether a person is in a room, you can already buy products using Qualcomm chipsets that have this capability. And there are also, but that's more using OFDM radar. There are startups that are using like OFDM radar to track, like in a healthcare setting, to track people and to make sure that they're okay, like in a kind of like senior care setting.
Yeah, so from my side, what I can say is the channel modeling is more like an enabler for designing new algorithms. And this basically enables a lot of ML-based methods that is under exploration. So that is one thing. About the neural augmentation, again, neural augmentation is a guiding principle that is used in a variety of ML solutions that we have. As you can see itself is not part of any product yet, but it is a guiding principle that we demonstrated in this presentation.
You both. And what if you tested the model inside a factory with a lot of metal?
There was the question about the active positioning for.
I think
in the warehouse, because that warehouse contains a lot of metal, and it works quite well. But indeed, that environment is challenging. So certain experiments, like research that we do, doesn't work as easily in this warehouse setting. But the demoed models obviously did.
And will these algorithms run on chipsets, or will it run on base station?
So at the end of the day, I think both are options. Of course, at the end of the day, we want to have intelligence on the edge device. So we want to be able to run it on chipsets.
Super. We have time for a few more questions. So if we can only observe pilots in certain non-continuous frames, DMRS and 5GNR, how do you improve channel estimation by machine learning?
That's an excellent question. So the problem, the 5G channel estimation is slightly different from the setup that we had here, which is a kind of the LTE continuous type transmission. In that cases, the problem, although Kalman might not be immediately used, although this is still a possibility, the challenge remains the same. And the idea is you have dynamics, and from a specific DMRS patterns, you want to be able to estimate the channel over the whole resource block that you have. And there, of course, you can use a lot of different machine learning algorithms for that, and Kalman can be used as well. But in the literature already, there are many interesting papers using convolutional neural networks and vision-inspired networks to attack this problem. But yeah, I mean, it is a very because we need to deal with again different dynamics. It remains a very similar problem.
Awesome, thank you. And I think we have time for one last question here. So what kind of performance improvements can be expected from neural augmented channel estimation? And would it substantially improve coverage or capacity of the site?
Yeah, I mean, at the end of the day, if you have better channel estimation, you can do a lot of things with it. You get better throughput, which means that you might be able to save your resources, for your communication, meaning that you can get you can choose your communication parameters in a way that is better for all the parameters that mentioned. Of course, the better channel you have, the less noisy channel you have, you're going to have better demodulation, better throughput, better decoding.
Okay, well, I'll have one last question then for the audience. So you spoke briefly about the factory of the future, and can you speak more to that? What are some innovations that you expect to see in the future?
Like the goal is like centimeter level accuracy positioning indoor for autonomous, for robots in this factory of the future, and that this factory can reconfigure itself, right? So parts can basically drive around all using 5G communication and 5G positioning. Yeah, so those are the developments I'm seeing, and we're working on to make them happen.
Yeah, I mean, what I can add here about factories is one thing that is very interesting is about smart factories is you're going to have a lot of sensors with low resources that gather a lot of information, making the digital factory happen. And in order to enable communication, we need to be very efficient in the way we build our communication systems. And these type of small ML gains can go a long way and can bring a lot of gain in those designs.
In the scenario that the traditional model, for example, Kalman filters, is not good enough to describe the reality, then when the neural augmentation does not give satisfying results, how easy is it to find out the source of the problem? How do you know that it is the Kalman filters that are not the appropriate modeling and not the neural network that chooses the wrong parameters?
Yeah, that's an excellent question. That actually highlights the importance of experiment design for a machine learning application. So in machine learning research, it's not only important to show that you have a gain in specific scenarios. You need to design additional experiments to verify that. So whether if for a specific data set something is not working properly, either Kalman nor neural augmented Kalman, then what we need to understand, we need to understand how this has deviated from scenarios where both of them were successful, and then trying to see how we can find the spectrum of intermediate, let's say, data set, intermediate problems, where we can step by step debug the whole pipeline. But this just goes to show that experiment design, picking proper data sets, plays a huge role in designing these models. It's not like you get a data set and train on it and then try to get your answers.
Thanks, Arash. Another question that I see that looks interesting related to MIMO-GAN. So for MIMO-GAN, it is more likely to simulate, is it more likely to simulate a certain channel model or a certain environment? But what should be used as the baseline to judge that the GAN is accurate?
So let me start by first saying, as you can see, the GAN is stochastically generating samples. So MIMO-GAN is a statistical channel model. This doesn't mean that this channel cannot become spatially consistent. If the traces that you gather, they have position information, for example, attached to it, we can add this spatial consistency by conditioning, let's say, our generative model on the position. So although this is a statistical channel model, it can kind of capture statistics of a certain environment as well. Now, how do we evaluate the GAN model? For the prototyping that we have done, which is based on standardized channel models, we knew the ground truth, but in field, we do not know the ground truth. So we have to come up with other metrics, communication probably related metrics, to see how well MIMO-GAN is performing. I think that's a very interesting question that kind of relates to an interesting question in machine learning about evaluation of GAN-based models, how we can evaluate how well different generative models are doing. But there, we need to really use domain knowledge again to come up with good metrics. What we, for example, monitored here was spatial correlation. We noticed that, okay, there are certain designs that do not capture spatial correlation properly, but our design did. And there are similar metrics that if you have end-to-end simulation, you can have access to other communication metrics and try to see how well the model captures intricacies of the environment.
Thanks, Arash. Here's a good question for Daniel. Do you foresee that wireless sensing on such use cases as intrusion detection and fall down detection, will that replace other sensor technologies in the future, or will they coexist?
Well, I guess they will coexist, but at the high end, you will start seeing the usage of these new RF-based techniques. For instance, for fall detection, to do that reliably, like at really medical grade, right? You really need better hardware. And obviously for consumers, it's going to be real easy to add this functionality to your existing Wi-Fi, your mesh network at home. But yeah, I see like an overlapping period and then eventually replacement by new technologies.
Great. And another question I see is kind of about future direction. So you guys, Arash, went into a little bit briefly, but is there anything further that you can say about where some of this AI research for wireless is heading?
I want to probably, we talked a little bit about this synergy between sensing and modeling, but I want to emphasize more importance of modeling and channel modeling at large. There are a lot of machine learning approaches that can be used in that area. Having good channel models is really crucial for designing good ML solutions and evaluating ML solutions. Otherwise, we can get a very generic statistical model and we don't see any gain from ML models, and we might misjudge and say, oh, ML doesn't bring any gain. That's an area where we can bring a lot of research from generative modeling, a lot of discussion about incorporating physics in the model in machine learning. So all those topics can be incorporated. And then if you add on top of that the nonlinearity, then it becomes really like a very exciting area for future research.
A few questions came in, just I guess on the setup for some of the experiments you guys did, and asking about the frequency. So just maybe a brief answer about, was this tested in sub-6? Was it millimeter wave? What kind of spectrum was being used?
So all the experiments that I talked about are like sub-6 gigahertz, so like 5.5 for the Wi-Fi, and then I guess 3.5 gigahertz for the 5G work.
Yeah, similar for us. We're sub-6, 3.5 gigahertz for all the experiments. Yeah.
That's great. And I guess there was also a question about the Neurochannel model. So are there Neurochannel models that are out in the public for people to test, or how do people experiment with Neurochannel models?
I mean, I think they're in the research community, there has been many interesting works on neural channel models, using different techniques for learning that. So the codes are available for those models. I would say the next step for these type of models is to have a good data for basically evaluating all these models on the same ground, and after that, we can probably have a better judgment about that. I would say first thing to evaluate, maybe the first step for evaluating such models would be using standardized channel models, at least because you have access to ground truth. So you can see how well your model is doing compared to other stuff. And then you did the algorithms and all that. They are specified in the papers, including our method was published in ICC, so you can have access to the paper and the simulation details, and similar for other works. That's the starting point, and the next step would be getting some real data and working on that.
Great. Well, I think with that, we're well over time. I'd like to thank both Arash and Daniel for the great presentation and the great answers. We'll be sharing the slides, and the webinar will be available on demand. So look forward to the next webinars, and thank you for everyone that came today.